Welcome to our first dripper quality seminar, a webinar that we're doing. We're going to start off with this one here, and there'll be another couple to follow. Here we're going to discuss dripper quality and features. And in front of you, you can see on the screen there it says engineering features for non-engineers. The reason that this is there is because we're trying to make it so that it can be understood by all who are attending. So I understand that maybe some of this may be a little bit too simple for others, but bear with us to the end, because at the end of the day, the features that we do discuss will have a bearing. In front of you now on the screen now, you see 5 dripper terms. Now, all of the literature that we give you, our technical people who hand out what we call the TechNet and the condensed product guide, you see encircled in the tables in front of you 5 features of a dripper. K, sometimes called A, X, sometimes called B, the KD, K, is the turbulence coefficient, and the filtration area. But what do they mean? Understanding these terms enables us to compare how our competitors, Netafim's competitors, do the same job. The first one we're going to look at are the 2 that lead to keeping a dripper clean. A good quality dripper can be defined as one that emits a predetermined flow rate that is accurate and constant over its intended lifespan. To do this, essentially, the dripper needs to be kept clean. And this involves 2 aspects: K, the turbulence coefficient, and the effective filtration area. And there I have highlighted them on the red, on the right side of the column. By the way, I've got to mention that if anyone has any questions, if you can click on, there's an icon on the top right-hand side of your screen, which has got Q&A there. If you can click on that, you're able to pose questions either as your name or anonymously. And at the end of this webinar, we will address your questions. Okay, so we've got the turbulence coefficient and the filtration area. Now, just to start off with, we'll just look at what pressure is. So just as car tires have got pressure using air, so too do dripper lines. And where tire pressure is normally about 2 bars, 2.5 bars, dripper line pressure is normally about 1 bar. Okay. Sometimes with certain drippers, what we call PC drippers, it does go over 1 bar to 3 or even more bars. But normally it's about 1 bar. And if you can just remember that 1 bar for later on, because that is a default setting on drippers. A dripper has a flow rate. These days, normally 1 litre an hour to 2 litre an hour, the normal type of drippers that we have. And it has an inlet pressure, as I said, normally 1 bar, and an outlet pressure, which is always 0 bars. Now, a dripper needs to reduce its inlet pressure from 1 bar to 0 bars, and still at the same time get 1 litre an hour through it. So something happens between the inlet pressure and the outlet pressure, and that's what we're going to look at now. Now, an easy way to deliver 1 litre an hour would be to simply make a hole. If we did that, the diameter, if we punch that into an average size plastic pipe, it would be about 0.17 millimeters in diameter. And this is just a pinprick. In perspective, 0.17 millimeters is a common width of a strand of some human hair. And it produces a jet, not a drip, so we don't want that. Plus, obviously, it stands to reason. If it's so small, the risk of it getting clogged is quite large. So another way to get away from the drip would be create friction loss. Create friction loss through a small pipe. Now, as water travels down a pipe, as I've shown diagrammatically here, it loses pressure. Now that is caused by friction loss. Now, if you are walking in a park or out in the veld and you see a stream or a canal or something like that, if you throw some twigs or grass into the water, you will see that the grass or twigs that land in the middle of the stream float downstream much faster than those on the edges. And that's caused by friction loss. Okay, the water, as it rubs along the side of the fixed object, in this case the walls of a canal or a river, it creates friction, and that reduces pressure. So as I put here, as water travels down a pipe, it loses pressure, and the longer the pipe, the more pressure is lost. So if I've just got here, we've got a pump here that's pumping down this pipe here, and it's 100 meters long, and where it starts off with 1 bar, it goes down to 0.75 bars. And then if we double the length, we're going to double the pressure loss. And that is what the first drippers did. In the early 1960s, this is what a dripper looked like. It was a small tube wrapped around a dripper line. That's all it was. Eventually, it became formalized into a molded dripper. And in 1966, Netafim manufactured the world's first dripper. By molding that, it still had the same principle into this barrel-shaped dripper that inserted into a dripper line. It was a cylindrical tube with laminar flow. What's laminar flow? Okay, if we just go back to that diagram I showed you earlier, and there you can see a canal. There you can see on the left-hand side, a smoothly flowing river, a canal, okay? Versus on the right, a raging torrent. That raging torrent is the turbulent flow. So there you can see turbulent flow versus laminar flow. And if I was to use an analogy here with keeping things clean, the laminar flow can be like putting your washing in a hand basin and letting it soak. And the turbulent flow, that's like putting it in a washing machine. So how do we get turbulent flow created in a dripper? That was simply creating teeth. So we went from the picture on the left-hand side of the screen, laminar flow, straight tube, into the one on the right-hand side where we put teeth. And that created the turbulent flow. Okay, that created from your tub where you soak into the washing machine. The teeth in the dripper creates the washing machine effect in a dripper. And that keeps particles in suspension. You can see on the bottom line there, as where I'm pointing to now, the water enters that side and it keeps all the particles that are in that water in suspension and doesn't allow them to be deposited on the walls of the dripper, and they exit and carry on through. Okay. With your laminar flow, that was not the case. Any particles that were in the water would be deposited on the walls of that dripper. Eventually, the turbulent flow dripper in 1970 was formalized, and that is it there. The turbulent flow dripper, again, was a barrel-shaped dripper. Nowadays, a modern dripper has changed its shape, and it looks more like that. This is what we call a boat-shaped dripper. Instead of being a barrel-shaped dripper, this top part of the dripper is welded onto the inside of the pipe that you see there on the top left. The pressure difference from the inlet of the dripper flow path to the outlet is explained by this equation, the equation on the left. For this presentation, the equation itself is not important. Safe to say that the pressure difference comprises two aspects: turbulence and friction loss. For those of you that are familiar with, that have studied fluid mechanics, that if you break up the equation on the left there, you'll find it comprises two parts, turbulence and friction loss. The friction loss itself comes from the Darcy-Weisbach equation, and the turbulence part of it comes from your local head loss equation, v squared over 2g, velocity squared over 2 times the gravitational constant. That's getting technical. It's not necessary, though, for the purposes of this presentation to know that. As long as you just know that the head loss comprises turbulence and friction loss. So in the dripper, we've got the top diagram there, which shows turbulent flow going through a pipe with teeth in it. That's your turbulence. In the bottom pipe there, the bottom picture, there's no turbulence. That's laminar flow. So basically, the pressure loss that goes through a dripper is a bit of the turbulence, a bit of this, plus a bit of this. We said earlier that a dripper has to create 1 bar pressure loss. The less turbulence the dripper can create, the more that dripper must resort to friction loss to create this 1 bar. So if you cannot achieve the required head loss through the turbulence, putting in your teeth, the more you're going to need the bottom situation. You're going to have to add friction loss. So turbulence, the more, the better. Friction loss, not so good, the less, the better. So the same equation that I showed previously, all I've done now is I've just taken the actual turbulence, the K part of it, and put it on the other side of the equal sign. That there, the turbulence in a dripper, is measured by the turbulence coefficient, which we represent as K. So the greater the value of K, the greater the turbulence coefficient, the better the dripper is at keeping clean. What affects this? How do we change the turbulence coefficient? The depth and the width of the labyrinth. The greater, the better. So if I take a common dripper, 1 litre an hour dripper, this is a Netafim dripper, it's got 44 teeth, and a pressure difference of 1 bar. It's got a width and a depth of 0.6 and 0.59 millimeters respectively. If we were to increase those dimensions by 0.01 of a millimeter, up to 0.61 and up to 0.6, our turbulence coefficient would increase from 7.2 to 7.7, so we'd have more turbulence. The length of the labyrinth, the shorter the better. If we took the same dripper as above, we put less teeth, greater turbulence, we added more teeth, smaller turbulence. Now, earlier on, I just said, what do we use to create turbulence? I said it was teeth. So you can get a bit confused here, because you might think, well, if teeth cause turbulence, then the more teeth, the better. The more teeth that you need, because we're still using the same amount of pressure loss. So if we had 44 teeth to produce that pressure loss, and now we increase that to 82, each individual tooth is less efficient. So now it means that our turbulence coefficient is going to reduce, in this case from 7.2 down to 3.9, just by almost doubling the teeth. If we take the same dripper as above, and now we're going to look at the design and manufacture of the labyrinth itself. If all the dimensions remain the same, the width and the depth, the number of teeth remains the same, but the head loss increases. Okay, we managed to get more head loss, right? This can only come from the actual design and or manufacture of the dripper itself. So with all those dimensions remaining the same, if we manage to increase our head loss from 1 bar to 1.2, we increase it by 20%, our turbulence coefficient will increase from 7.2 to 8.7. Now, how do we do this? Let's have a look at the labyrinths through the ages or in the last 20, 30 years or so. The labyrinth design on the left shows rounded edges. And then as we move along to the right, we're getting better and better and better. Okay, the turbulence coefficient of each of these designs is getting better and better until we wind up on the very right-hand side of the screen where it says Turbulence. The first one, we've got rounded edges, where I'm pointing to now. The next one, we get those rounded edges, and now they become teeth, sharp, sharp teeth. But you can see that these teeth are kind of like meshed with each other. So you can see that what we're kind of creating here is like a windy canal. Okay, so we're having less turbulence. Then if we pull apart those teeth, and we get the middle diagram where it says the line teeth, okay, now we're getting better turbulence. And then if we break it apart even more, we're getting what we call the turbonet. The generation of drippers before the generation we have now had the turbonet. And then what we did is we changed the angle of those drippers so they weren't coming off at right angles like that. They were angled, and that became the turbunext. Let's have a look first at these rounded edges. The rounded edges create less turbulence than razor-sharp edges. Rounded edges can come from, firstly, the actual injection molding process, not expelling all the air in the teeth. And secondly, by the second part of the process, when we're actually welding that dripper to the pipe. So where I point to now, if I look at here, where my cursor is, if you can imagine molten plastic is flowing down the mold to create that tooth. At the same time, it's expelling air. If we don't manage to expel that air 100%, we're going to wind up with a rounded tooth there. If we get it right, then we're going to get a razor-sharp tooth. And then, as I mentioned, the other part of it comes in where a possible rounding can occur is when we weld that dripper to the wall of the pipe. When you weld anything to anything, you're going to get a distortion. And the minimum that you can keep that distortion to, the less rounded will be, in this case, these teeth. So let's dwell a little bit more on this subject here. There's quite a lot written on this slide here. If the design and the manufacture of the labyrinth is not optimal, the less turbulence is going to create it, and the more the dripper will need to resort to friction loss to achieve the 1 bar pressure loss that is required. So what I said earlier, okay, the less turbulence we're going to need, the more we're going to need of friction loss. So now on the left-hand side of the screen is a Netafim Typhoon dripper. The yellow dripper below is a copy of that Typhoon dripper. The required 1 bar pressure loss has not been achieved by the yellow dripper with this labyrinth in the design. The people manufacturing didn't get it right. They didn't get razor-sharp teeth. They didn't get the design of those teeth right. So it has had to resort to more friction loss to create that 1 bar. So more teeth have been added and the labyrinth is longer. Okay, so those two drippers there, on the left and the right, they both produced 1 liter an hour and they both produce it at 1 bar pressure. Okay, but you can see that the filtration area, which is, as I say here, it results in double punishment, is not only in the yellow dripper have we got the longer labyrinth, but the dripper filtration area is now smaller. And that we're going to get we're going to move to in part 2. The point I'm trying to make now is you can see here that because these teeth in this yellow dripper are not of the quality they are in the black dripper, therefore more friction loss has had to be resorted to. That is created by a longer flow path, and that is why you can see a 50% increase in that flow path length. If we just have a look at this more closely, the dripper on the bottom left is a Turan dripper. This was the generation before the current Aries dripper, but I'm showing you the principle here. If you show up on the left, I've blown up one of the pictures, and as I say here, if you cannot achieve these razor-sharp teeth, then as I go on the right, let's have a look at the blow-up picture of the competitors. You can see they're rounded. They're not razor-sharp like these ones here on the left. So if you cannot achieve this razor-sharp teeth, you have no option other than to increase the number of teeth or to narrow the labyrinth by its depth or its width, or both, as the dripper on the bottom, as the bottom right has done. So again, it's showing the same principle, not being able to get the rounded teeth, not being able to get the razor-sharp teeth. Now, when we look at this in comparing drippers, not all drippers are used for the same purposes. We've divided things up into class 1, 2, 3, 4. The numbers don't really mean much, but what is important is the description. A class 1 dripper is a pressure compensating dripper and it's got to last over 10 years. That's the sort of thing we use in orchards. We use it on varying terrain, slopes, goes long distances. We also use it in water of questionable water quality. The class 2 dripper is the same dripper, but now it doesn't have to last as long. It doesn't have to last over 10 years. It's not going to go into a citrus orchard, something like that. It's going to go, so for instance, subsurface sugarcane. Then on the right-hand side of the screen, we go into the class 3 and the class 4 drippers. The class 3, and these are now non-pressure compensating drippers. So the class 3 is similar to your class 1, but just a non-pressure compensating version of that. So it's a non-PC dripper, but it has to last over 10 years. And of course, it doesn't have the ability to handle the slopes distances to the degree that the class 1 dripper can. And then your regular or your standard non-pressure compensating dripper is the same as class 3, but now it doesn't have to last 10 years or more. Now, if we look at Netafim's family of drippers or range of drippers, how they fit into the classes, your class 1 is the high-end pressure compensating drip. That's our Uniram. The standard one is the DripNet PC in all its variants, PC, AS, but as the family, the DripNet PC family, that's your class 2 standard PC dripper. And then in the non-pressure compensating drippers, at the high end, we have Aries. And then your regular non-pressure compensating drippers, your Typhoon Plus, and Streamline X. Now, how do these compare then in turbulence coefficient? How do these compare with our competitors' drippers? So what I've put here, I've taken the Uniram dripper, I've just taken one flow rate, 1 litre an hour. The Uniram dripper has a turbulence coefficient of 10.4. Now, if I take one of our competitors, and I've taken 3 competitors and named them A, B, and C. If I take manufacturer A, their high-end dripper, it's got a turbulence coefficient of 9.4. Why is that? Well, you can see I've highlighted in red there. Okay, here, it's got 55 teeth. Then I've taken 2 other competitors, B and C. There, they have got turbulence coefficients of 0.9. Okay, call it 1. Why is that? Well, the depth and the width has been reduced. And more importantly, with this design that's got, and it's got a similar number of teeth in us, but why is it only 0.1? With this design, the flow rate is not 1 litre an hour, it's 1.2 litre an hour. So based on that, if you took that design, if they wanted to produce that dripper at 1 litre an hour, one would presume that they'd have to either add teeth or they'd have to narrow the width and the depth even more. Similar with manufacturer C. Okay, they've got a better turbulence coefficient and a similar number of teeth than us. They've actually got 2 less than us, and the dimensions are much the same as us. But the turbulence coefficient is less because with all that, the flow rate is 20% higher. It's 1.2 liters an hour. So again, based on the same rationale, one would assume that with that design, if they wanted to bring that down to 1 liter an hour, they'd have to reduce some of those dimensions or add number of teeth. Then if I take DripNet PC, the 1 liter DripNet PC has got a turbulence coefficient of 10.8, and manufacturer C, their one comes down, the turbulence coefficient comes down to 3. Sorry, I skipped there. It comes down to 3. And why is that? Well, as I've highlighted in red, the dimensions are less and the number of teeth are greater. Okay, and then company A, and these are all real drippers in the market. 0.56 and 0.8. The 0.8 is actually greater than our depth, but then look at the number of teeth. Got 119 teeth, and that's what brings that turbulence coefficient down to 4.2. Then if we come to the non-pressure compensating drippers, our high-end one is Aries, which has a turbulence coefficient of 5.9. And then if I look at our competitors, where we come down to 3.7, the one beneath it. Why? Well, the depth and the width are less. And the one below, where in the bottom there, it comes right down to 2.3. Why is that like that? Because the number of teeth has rocketed up to 160. And then I look at the non-PC, Typhoon, and Streamline X, where we have turbulence coefficients of 7.2 and 5.8 respectively. Now, company B, they've got quite a good dripper there. You can see it's got 7.1. But with these dimensions that they've got, again, we're going up, we're increasing the flow up to up 20% to 1.2. So again, based on what I said before, if we're going to bring that down to 1, presumably they'd have to bring these dimensions down. The same with C here, as we've seen up in as the same as with the pressure compensating drippers. The lower turbulence coefficient is because of the lower width and the depth, or in this case, in the very bottom one, the lower, the higher the number of the teeth. So we say, okay, so big deal. How's this affect me? How does this affect our farmers? That's the most important. What is the impact of the turbulence coefficient on the farmer? The farmer and his crop care not about the specifics and technical details of a dripper. Their only concern is what the dripper delivers. They need a drip supply of water and fertilizer into the root zone on demand during the lifespan of the crop. This drip supply must never vary nor decrease over time. It must be accurate and constant over the crop's lifespan. So that means if we got a 1 liter an hour dripper when the crop is planted, depending on the lifespan of the crop, if it's 10 years or if it's 15 years from now, it must still be delivering 1 liter an hour. And essentially, it must be kept clean. And that, as we have shown up, as we've seen above, is done by Turbulence. On you as the irrigation company, a system that does not meet this criterion will need rectification. That's time and money. So if I can summarize, we've seen that we need to create pressure loss, and that pressure loss is turbulence and friction loss. We want more turbulence and less friction loss. Turbulence is measured by the turbulence coefficient, K. The greater the K, the cleaner the dripper. Turbulence coefficient K depends on the labyrinth depth, width, and length, number of teeth, and its design and manufacture. Now, before we go on to the end here, I just want to emphasize that, well, firstly, If you've been looking at the slides above where we stated our competitors, and say, well, who are those competitors? We can discuss those with you, and those will be between you and your irrigation technical advisor from Netafim, who will be able to explain this and show this one-on-one with you. I just wanted to more here to focus on what are the factors that contribute to the turbulence coefficient. That's why I put just A, B, and C above. Another thing, and you will see that in everything I've shown you above, is that Netafim has always got the highest turbulence coefficient, and a reaction is, well, where does the turbulence coefficient come from? You know, did we make this up? No, we didn't. As I mentioned just earlier, okay, that turbulence coefficient comes from two basic fluid mechanics formulae that I mentioned earlier. And if anybody wants how that turbulence coefficient is derived, I'll be happy to send them a paper that shows how it's derived. So in the next webinar, we'll get onto the filtration area, and those are the two factors that lead to keeping the dripper clean. I'm now going to switch over to questions. I'll stop sharing my screen. And we'll have a look at the questions that have come up. Okay, the question says here, does the efficiency of the dripper deteriorate over time? Is this material susceptible to wear? Well, the answer to that is yes. It is possible that you can have abrasion, but will that occur inside the dripper flow path? If you break down and have a look at the actual velocity through that flow path, it is it's minimal. In fact, if you have a look at that velocity, it's actually laminar flow. Okay, so but the actual turbulence is created by the actual keeping up in suspension. The longevity of the drippers is actually more dependent on the actual maintenance, and it's going off subject here, but the actual most of the deterioration or abrasion that actually occurs on the wall of the dripper line, the outside, before any abrasion occurs inside the pipe. So generally, if you have a look at a dripper line that's 10, 15 years old, you can see all the abrasion on the outside. Hence, that's the rationale behind why we say use a heavier wall thickness for the longer crops and a smaller wall thickness for the smaller crops. But the actual effect on the dripper it's very minimal. Does water quality influence the effect of turbulence? That's actually a good question, which I haven't really thought of properly. In terms of the water quality, you've generally got to have good filtration. At the inlet to a dripper, there is a filter, which the larger particles, the ones that are likely to affect this, cannot get into the dripper. And when I just think about this, the larger the particles, if they do get into the dripper, yes, they will affect the turbulence, and they will reduce the turbulence. That's how my logic would say it to me. But there is a filter, which we'll be getting on to the next time, that does prevent those larger particles getting into the dripper. Are companies obliged to publish their K and the number of teeth per dripper? Okay, well, I can't speak for other companies. is. For you as the irrigation designer, you actually don't need, in your irrigation design, you don't need to know K. You don't need to know the number of teeth. It doesn't affect your actual design as such. Okay. The guy designing it, the Netafim guy designing the dripper, he needs to know that. He'll design a drip and have a look at the teeth and the turbulence coefficient, but that's where it stops. This turbulence coefficient is purely being done as a means of comparing drippers with drippers. Okay, to having a look at, as I mentioned, we've got a 1 bar pressure going in, 0 bit going out. Something happens in between. Okay, so we've done this to explain what happens in between, and this is the result. So it's something so that we can look something that is measurable, and that's why we publish our turbulence coefficient. Okay. Fellow irrigation colleagues, thank you for your time. This is, I appreciate the attendance that we have. I hope that something has been picked up. That's the last question that we have got. And stay safe and God bless.